Welcome back to 30 Days of Physics with Miss B, and we're moving right along into day 6, springs. Springs are present in many devices and appliances that we use, such as retractable pens, spring beds, and cars. In the 17th century, springs were investigated by a man named Robert Hooke. He found that the extension of the spring was proportional to the stretching force as long as it was not permanently stretched. This means that doubling the force doubles the extension, trebling the force trebles the extension, and so on and so on. According to the information above, what would be the extension of the spring if it has a mass of 200 grams affixed to it? You may pause the video right here. The answer: if 1 Newton causes the spring to extend by 10 centimeters, then 2 newtons would cause the spring to extend by 20 centimeters. As you can see, doubling the force doubled the extension. Hooke's observation was then made into a law. The force applied to a spring is proportional to its extension. Expressed mathematically, Hooke's law is force is equal to some type of spring constant times extension. The spring constant represents the size of the force required to stretch the spring by 1 meter. It is a measure of how stiff the spring is. A high spring constant represents a stiff, tight spring. Once the spring does not stretch out or get damaged, a straight line graph of the results can be obtained to determine the spring's constant K. The unit of the spring constant is newtons per meter. As you can see by both graphs, we have one curved down and one curved up. In the first graph, you have force against extension. In the second graph, you have extension against force. This is totally dependent on what you are trying to judge and what you decide to keep constant. Remember, all constant variables are placed on the x-axis. Everything else that you're trying to judge is placed on the y-axis. Please note, for a graph drawn for force against extension, the spring constant will be equal to the gradient. However, for a graph drawn for extension against force, the spring constant will be equal to the reciprocal of the gradient. Hooke's law only applies up until a point called the limit of proportionality. If the load is increased after this point, the spring will continue to extend, but the additional extension will not be in proportion to the force applied. The spring is therefore no longer behaving like a spring. Between the proportional limit and the elastic limit, the spring will be able to return to its original length. This is referred to as elastic deformation. If the spring is stretched further than the elastic limit, then it will become permanently deformed. There is no going back. This is referred to as plastic deformation. This means that it will not return to its original length ever again. The area between the line of the graph and the x-axis that is within the proportional limit represents the potential energy stored or work done on stretching in SI units of Newton meters, which is equivalent to the joule. To determine the work done, all you have to do is find the area of the triangular section right here. Elastic bands or rubber bands do not obey Hooke's law. They do not produce a straight line graph, and heat is given off in the process. This is a graph that is produced by elastic bands. Let's try this question together. A spring is loaded with a 2 kilogram mass, and its length increases by 20 centimeters. The original length of the spring is 60 centimeters. A. What is the force constant of the spring? B. The load which will stretch it to 100 centimeters. You may pause the video right here. Please try your best at this question and then proceed. Don't give up now. Answer to part A. We are solving for the spring constant K. Force F is given 2.0 kilograms times 10 newtons per kilograms to give you 20 newtons. Extension X is given 20 centimeters, which can be converted to meters, 0.2. If force is equal to the spring constant times extension, then the spring constant will be equal to force divided by the extension. We divide 20 newtons by 0.2 meters and we get 100 newton meters. Answer to part B. We are solving for the load required to cause the spring to stretch to 100 centimeters. The original length of the spring is 60 centimeters, hence it will be extended by 40 centimeters to reach to the 100 centimeter mark. If 2 kilograms makes the spring stretch or extend by 20 centimeters, then X kilograms would make it stretch by 40 centimeters. X will be equal to 4 kilograms. Remember, 1 kilogram is equal to 10 newtons. Hence, the load required to cause the spring to stretch or extend to 100 centimeters would be 40 newtons. Here's another way to answer part B. We are solving for the load required to cause the spring to stretch to 100 centimeters. The original length of the spring is 60 centimeters, hence it will be extended by 40 centimeters or 0.4 meters to reach to the 100 centimeter mark. Using force equals the spring constant times extension, where K was already solved and found to be 100 newtons per meter, X is also equal to 0.4. X represents extension, and F is to be calculated. We can simply substitute. Multiplying 100 newton meters by 0.4 meters would give you the same 40 newtons. Alright guys, thanks for watching 30 Days of Physics with Miss B. It's day 6 and it's been great. Don't give up now. Keep on striving. Look out for my new video, day 7, coming soon.